Okay, so we're recording now. Right, so as I said, from this morning, I'm going to be broadcasting the lectures on Zoom, and they're going to be recorded. But the idea is still the lectures will be given live on the whiteboard, and the presentation of the lectures is going to be geared around a live presentation on the whiteboard, not around presenting in a nice way on the computer. So if you watch live, you probably won't see everything, and also the videos are not going to capture all the material. Having said that, today's lecture is going to be different, a different format. So today I am going to write computer notes on the screen, and the reason for that is I had an operation on Friday, a small operation on my back behind the shoulder blade, and I need to, it's okay to write like this, but it's not okay to be, I need to rest my shoulder, so I can't write on the board this week, maybe next week as well. I need to wait and see how things are next week. But anyway, certainly this week is, so I'm afraid it's going to be a bit like an online lecture, but in the class, at least we can see each other, but I'm going to be just writing on the tablet. And the good thing about it is the screen, if I'm sitting here, the screen is really offering the maximum protection. So for people sitting in this direction, at least. Okay, so today's lecture 2. And what we're going to talk about is the mathematical model of computation that the whole course is going to be based on, and that's Turing machines. So the topic today is a very famous mathematical model of computation called Turing machines. And these are called Turing machines after the very famous British mathematician and code breaker during the Second World War, Alan Turing, who introduced these machines in a 1936 paper that has a very long and complicated title. So I won't say the title, but I shall actually put a copy of the paper on the course webpage so you can have a look at it. So I'll just say these were introduced by Alan Turing in 1936. So Alan Turing had a bit of a colourful life. So in his 20s, he defined Turing machines and solved one of David Hilbert's 20th century challenge problems, the Entscheidungsproblem. I don't remember which number it was on Turing's list. So he made a great mathematical breakthrough with his introduction of Turing machines. Then in the Second World War, he was involved in a place called Bletchley Park in Britain, where he was breaking the German codes, and apparently the work that his group did, people have since evaluated as being responsible for considerably shortening the length of the Second World War. After that, he did many things, but he went into building some of the first digital computers. So he was actually constructing computers, but he's also known as being a victim of the British law at the time. So he was a homosexual, and he was prosecuted for his sexuality and forced to take some punishment of well, I don't remember exactly, but in any case, he ended up dying very young. People think he committed suicide. There was a bit of a sad end, and actually people only found out about the work he'd done during the Second World War years after his death, because it was classified. It was secret. It was only released, open to the public, that information 25 years after it happened. So Anyway,
by the way, his punishment was chemical castration.
Right, so his punishment was chemical castration. Maybe for the almost almost unprecedented thing, the British government actually apologized for this about 10 years ago. And he's now a hero in Britain. And he was last year or this year, he was the face on the new, I think it was £50 note in Britain. So I don't know if, I was going to say maybe one of the only benefits of Brexit that we got Alan Turing on a note, but actually I don't know if it's got anything to do with Brexit or not. Anyway, so Alan Turing designed the notion of a Turing machine, and he did this in the 1930s before digital computers existed. But his motivation was to, so let's write it down, that his motivation was to provide a precise mathematical definition of the notion of algorithm. Does anyone mind if I shut the door now? We've got a window open, just because this noise is. So the motivation at the time, well, and it's still the motivation. So give a precise mathematical definition of what an algorithm is. Nowadays, perhaps everybody has a better informal idea of what an algorithm is than they used to 100 years ago when, well, 90 years ago when Alan Turing was thinking about this, because now we're all familiar with computers. We've had the technology for years. Most of us have experience with programming languages, so we think of an algorithm as something we can write a program. Well, an algorithm is the process that a program we will write will undertake in performing its computation. But 100 or so years ago, when Turing and other people were thinking about this, people didn't have computers. So they were extrapolating from the idea of what humans do if they have an algorithm to follow, a precise specification of a computation process. And in order for Turing to solve this problem of Hilbert's, this Entscheidungsproblem, it was crucial in order to do that, to be able to say, this is a mathematical definition of what an algorithm can do. Around the same time, several other people came up with other precise mathematical definitions, but they all turned out to be equivalent. And the notion of Turing machine is that's the model of the notion of algorithm that we're going to use in this course. So it's equivalent to the other ones, but it's rather a nice model because one can see from the model itself in what way so the model itself is built, but there's a nice story behind it about how it gives a model of the notion of algorithm. And it's also relatively simple to define. So there are now many other such models. Actually, most of them were developed around the same time. But all are equivalent. So there's a little caveat here about all being equivalent to do with quantum computation, but we won't go into that now. So we're going to use the notion of Turing machine because it's a simple, so it's a simple model, but actually for the purposes of the course, it wouldn't really matter which model we took, just if we took a different model, the definitions would get a bit more complicated. Right. So we're going to see what a Turing machine is. Probably many of you have seen the notion of Turing machine before. So then there's not going to be very much new in this lecture for you. But before seeing the model, I want to present the design criteria that, so Turing, when he was writing his paper, people had not really done such a thing before. So he wanted to come up with a precise mathematical model, but also explain to the readers why his mathematical model really was a nice, plausible model of the notion of computation. So he wanted to start with an informal consideration about the computational process, about if somebody has an algorithm, what sort of things they would need to be doing, and use that informal, use these informal considerations to say, well, these informal considerations are precisely reflected in my precise mathematical model that I'm creating. So, so he wanted to formalize the notion of algorithm. And so I'll come back to the top bit in a moment, but he had the following thoughts. So an algorithm is a precise description of a computational process that for example, person that wants to follow the algorithm to calculate through the algorithm should be able to follow the finite description, but so to the precise description. But in order to have a precise description in front of you, firstly, it needs to be finite. So there's you can't expect to present an infinite description to somebody. So an algorithm should be some finite description of a computational process. And he's thinking of algorithms here, like the classic ones in mathematics, such as Euclid's algorithm for finding the greatest common divisor of two numbers, which is well known as one of the first algorithms that appears in the human mathematical literature. So such a thing, there are a finite set of instructions. These are the steps you need to follow. And those instructions are very precise. So the algorithm specifies the entire computational process. So there's nothing that's not in the finite description that one needs to do in the algorithm. The algorithm contains, the finite description of the algorithm contains all the information about what one needs to follow the process. And moreover, the actual process of following those algorithmic steps that are specified for you, they should not require any creative input. So you don't need to solve any difficult problems or something like that. The whole point of the algorithm is the person writing the algorithm, or the algorithm itself, is giving all the instructions, and then you don't need any intelligence to follow it. You just need to be able to follow the instructions. So reasoned Turing, I mean, this is basically his process that you can, his thought process, his argument that you can read in his paper in nice English prose in his paper, but I've condensed it to some bullet points here. So given that, so it's a process that there are these instructions that specify everything that the algorithm is going to do, and one can follow them without any creative input. Therefore, they can be followed by a machine that does not need, this was before the days of artificial intelligence. And actually in my resume of what Turing did in his life, I forgot to mention that he wrote a very, very important paper about artificial intelligence at the time that he was one of the first people to consider the idea of artificial intelligence. So I forgot to mention that. But here we don't need an intelligent machine. The point is an algorithm is sufficiently routine, specifies all the steps that it can be carried out by just a simple machine that follows instructions. And then how's the machine going to work? Well, like anything on this world, it's going to calculate. I mean, if it's calculating, but like anything on this world, it's going to have to work in time. It's going to take some time. and it's going to have to work in space. Right? We're in the physics building, so we can say it's going to have to work in space-time if we like. But in any case, it's going to take time, and the algorithm will perform some steps. Each one will take like some small amount of time. And so when a human is following an algorithm, we tend to, so for example, performing some calculations, we tend to use some sheets of paper or something like that to write the calculations on. So just in the same way, we can imagine that the machine that's going to be following the algorithm will need some space, some working space, in order to make its calculations and to write them down and to be able to refer to the results of the calculations it's doing as it goes along. The machine is going to perform in time and space, and we don't know for how long in principle. We're following an algorithm. If you follow an algorithm, it might say, do this, do that, do something else, go into this loop, and every time round, do a certain thing until some condition is met. But perhaps that condition, it might be a little bit hard to predict how long it's going to take until the time that the condition is met. So in principle, one can give a description of an algorithm without bounding how long it's going to take or how much working space we're going to need. We might need to keep on getting extra sheets of paper to do our calculations for an unforeseeable amount of time. Although, of course, at the time that we finish, if we do ever finish, then at that point, we will have taken only a finite amount of time to that point that we stop, and we will have at that point only used a finite amount of working space. But still, to have the most general notion of algorithm, we don't want to bound the amount of time and space we're going to take in advance. Although in this course, we're going to be talking about algorithms that do work within the confines of a certain amount of restricted time and space. So quite soon we are going to look at, so the general notion of algorithm might use some arbitrary amount of time, might go on for a very long time, might use some arbitrary amount of space, but the point of this course is very quickly going to be, what can we do if we restrict the amount of time and space to a reasonable amount of time and space, such as polynomially bounded in the size of the input or something like that. But because time and space are going to be important, let's highlight these here. So nowadays we could basically think of an algorithm as equivalently a process given by a program we write to run on a computer. So programs to run on the computer basically satisfy all these conditions. Apart from if you're running on a real computer, then you really do have some bounded amount of time, which is how long you're prepared to wait for the computer to give its answer. And you have some bounded amount of space, which is what your computer has available. Although, of course, nowadays you might use the cloud or something like that to help you. You've got sort of quite a large potential amount of space available. But apart from real world restrictions on time and space, which of course always exist if we're doing something in practice, this is pretty much, one could basically think of an algorithm as something we write a program to do. However, this is a mathematical course and we want to prove consequences of our definition. So we want to be able to prove that, say, a certain problem has an algorithm that works in a certain amount of time, and moreover, this is optimal for that algorithm. So there's no faster algorithm or no algorithm that takes strictly less space or something like that. And to be able to do that, one really needs to have a precise mathematical model. And if you take, say, for example, the computer on my desk, it's a finite thing. I could perfectly well give a precise mathematical model of that, but as you could imagine, it would be very, very complicated. And the point of the Turing machine is it's a very simple mathematical model. And ultimately, it's equivalent to any other mathematical model of computation modulo the bounded potential bounds in time and space, but it's basically equivalent to any other model of computation, but this is a simple one. So in modern terms, the way of thinking of a Turing machine, so a Turing machine is going to be a machine that performs one specific algorithm. And if we want a different algorithm, then we'll change the Turing machine to a different machine. So you can think of that as like a computer with a single fixed program that implements the algorithm, or more briefly, we can just think of that as an algorithm itself. Okay, so those are essentially Turing's design criteria. And here is an example Turing machine. So it's best to explain the notion by starting with a particular Turing machine. And so we're going to look at this Turing machine and understand what it's doing. So a Turing machine is going to work in time and space. It's going to have some working space. It's going to have some precise instructions to follow. And there's a finite description of it. So here the finite description is this part at the bottom. So these 9 lines down at the bottom with these arrows in, this is called the transition function of the Turing machine. And these specify how the Turing machine is going to compute. The Turing machine is going to compute by, it has some working space available to it. So the way Turing thought of it, so we have a nice concrete model in mind here, that the working space is given by a tape, like a paper tape, divided into cells or squares. And on each square, you can make some annotation. And what you can write on an individual square will be given by some finite alphabet, as it's called, of symbols. So you have a finite set of symbols that you can write on the squares. So here, my alphabet consists of the letters little a, little b, and Turing machine tapes are always, the squares are always allowed to be blank. And the idea is actually when you start with the process, most of the tape is going to be blank, so the idea is you're going to start the computation process with the tape in which you've got some input, which is a finite sequence of characters from your alphabet. So here my input is the string A, B, A. So that's 3 symbols from the alphabet. We're going to compute with that, but we have the input written in consecutive squares on the tape, and the rest of the tape is blank. And the rest of the tape is like our working space for the computation. And I'm going to allow it to stretch to infinity in both directions. And the idea here is that it's an unlimited amount of space that we can work with. So we're never going to use all the infinite amount of the tape, but we've got as much tape as we want, potentially both to the left and to the right. Okay, so we have a tape alphabet, which is part of the specification of the Turing machine, which tells us the symbols we can have on the tape. It always contains, oh, sorry, I wanted this to be black. Always contains blank. So the tape alphabet here is the symbols little a and b, the letters little a and b, and I'll write a box or the blank symbol. So when we start the computation, all except a finite number of squares on the tape are blank. This is the blank square. I'll just write blank. So we start the computation on a given input, but we can run the machine on any number of different inputs if we want. So the idea is the machine is our algorithm, and the input is the input, or program, if you like. The input is the input we're giving to the algorithm. We'll run the machine on this input, and we'll see what happens. So to run the machine, we always run the machine. Well, to run the machine, we basically run through what's called a sequence of configurations of the machine, starting in the starting configuration. So the starting configuration has the input written on the tape. The machine has a head, as it's called, which is a read-write head. It looks at one. So the head is always in a certain position. I want to actually draw it closer to the tape because I think it'll look nicer there. So it's always positioned on a certain square. And what it can do is read the symbol from that square, look at the symbol on that square and only on that square. And it can also potentially rewrite the symbol on that square. So at the start, in the starting configuration, the read-write head is positioned on the leftmost character of the input string. Okay, so here the read-write head's positioned on the leftmost character of the input string. And we start, the machine is always in one of a number of a certain number of a finite set of states. So part of the information we give for the machine is something called the set of states that we can be in, which allow us to control the behavior of the machine. And there's always going to be a distinguished state called start. And when we start the machine, the read-write head is at the left end of the input and the machine state is in the start state. Okay. So part of some of the other information that we give then is a set of states. This is typically called Q. And here the finite set of states for this machine is we have the start state, as we always do. It doesn't need to be called start, it could be called something else, but you have to know, you have to have one state that is the state you start in. So we've got the start state. Then actually, if we look down at the set of transitions here, the instructions, we'll see that the other states we have are called next B and next A. And two other states called accept and reject. And this is all the states for this machine. So when we're specifying the machine, what we should really do is give the tape alphabet, which must contain the blank, but contains some other symbols, the set of states of the machine, and the transition function that tells us how the machine is going to compute. And now we're going to look at how the machine computes, and it's really very simple, so it's not going to take very long to work this one, run this machine through. So basically the idea is you're always at a configuration. At the moment, we're at the starting configuration. In any configuration, to see what to do, you look to see what the symbol the read-write head is, what symbol the read-write head is currently looking at. So it's currently looking at A, and we're currently in state start. So we look through the transition function to see if there are any transitions, and there should be at most one, because it's a function. So if there are any transitions that have the state start and the tape symbol that's being looked at as being A. And indeed, we see that's the first one. So we're going to, so this says, if we're in state start and the current symbol is A, then we move to state, we change the state to state next B. We put A on the current place on the tape, and we move the head by +1. So we move the head one step to the right. Okay, so to make this step, state changes to next B. we write an A to the tape, but there was where the head currently is, but there's an A already there, so we don't need to do it, don't need to change anything there. And we move the head one to the right, and then we're in the next configuration. So now we're in the configuration after the first step of computation. So I know I'm going quite slowly, but the point to emphasize here is we've made one step of computation. And when we're going to be counting when we're going to be counting the time that an algorithm takes, basically with a Turing machine, one of the nice things, we can just do that in a very simple way. The time the algorithm takes is the number of steps of computation we take until we stop. So far we've done one step of computation. Now we're in a B, and I didn't write it very well, but the state we're at here is next B. So we look to see when we're at next B, if we're looking at the symbol B, then we switch the state to next A. We write a B to the tape at the current position, so we leave the B in place, and again we move one step to the right. So now we go to next day. So this is whoops, I erased the box by mistake, but let's make it a bit bigger so I don't erase it. So this box is recording the current state of the computation. Now we're moving to next day. We leave the B in place and we move the head one step to the right. Okay, so we've now made two steps of computation. So now the head is in this position, it's looking at an A, we're in state next day. So in state next day, we're looking at an A. We see that we change the state to next B, we keep the A on the tape, so we haven't actually changed anything on the tape, and we again move one step to the right. So this is the third step of computation now. We change the state to next B. We leave the A on the tape, and we move the head one tape to the right, one square to the right. Now the read-write head is here, so now we see a blank on the tape. We're in state next B, and we see a blank. So we look to see if we've got a transition for that. We do. If we see a blank and we're at next B, then we move to state accept. We leave the blank on the tape, and the 0 means we keep the head where it is. So we go to state accept. We leave the blank on the tape and we leave the head where it is. So now we're in state accept. So we're in state accept and we have a blank on the tape. We look to see if we have a transition from state accept with a blank on the tape, but we see we've got no transitions from state accept. So that just means the machine stops. And the machine stops, and if I counted them correctly, we made 4 steps in our computation process. Okay, so we've done a simple computation. The machine stops in the state accept after 4 steps of computation in this case. And notice that accept and reject are special states here, in that there are no transitions from configurations in which we're in state accept or state reject. So whenever we get into either of those 2 states, state accept or state reject, then the machine stops. So these are accept and reject here are what are called halting states. By the way, I'm going to put these notes on the web afterwards. So today maybe it's not so important to make your own notes, but I should have said that at the beginning, but you're welcome to make your own notes. Okay, so here we ran the Turing machine on the input ABA, and we ended up, and the machine was in the state accept. If we had run it on ABB instead, then when the head had been here, we would have been in state next. So in the third position, the state would have been in next B, like it was when we were in the third position. Sorry, next A. The state would have been in next A when it was here. And we would have been looking at a B if we'd been running it on ABB. And we see that if we're on next A and we see a B, then we go to the state reject. So if we had run it on ABB, we would have ended up stopping in state reject rather than state accept. And this Turing machine is illustrating already a very important kind of computation, which we're going to, which is almost going to be the main focus of this course, because a lot of computational problems fit into this. We're running a computation on a string as input, and we're interested in whether the machine tells us that it is accepting the input or rejecting the input. So it's a way of dividing the set of all strings over the alphabet that we're using for inputs into two classes, those two complementary classes, those strings that are accepted and those strings that are rejected. So you've had a little look at this. Can anyone tell me what strings of A and B symbols, so if we're looking at input strings consisting of just A and B symbols, which finite strings of A and B symbols lead to an accept state here for this machine?
So they need to iterate, so A, B, A, B, A, B, it's fine, right? But
that's fine, yes.
Yeah, that's in the case if A is repeated several times or B is repeated several times, it's not okay. So
that's right, exactly. So strings of alternating symbols. So it doesn't matter what letter you start with, but once you start with a B, say, then it needs to go B, A, B, A, B, A for as long as the letters come. Doesn't matter how long the string it is, how long the string is, but the point is, if it's a string of alternating symbols, then it gets accepted. If it's a string that contains any symbol that appears twice in a row, then it gets rejected. So we say this machine, so let's write that down. So the same symbol must not appear consecutively. Okay, so that's somehow an informal view of a Turing machine. We've seen how it executes. If one wants to give a precise mathematical definition, then one has to encode this in mathematical terms. I don't want to spend too much time on doing this. So I think it's quite intuitive how it is. I just want to tell you what data you need to give if you're specifying a Turing machine. So in order to give a Turing machine, so what we need to specify is the tape alphabet. So that's a finite set of symbols that we can put on the tape. So the point is, everything with a Turing machine is finite apart from the tape itself, which is infinite, and that infinite size of the tape represents a potential that there's an unlimited amount of space that can be used. You only ever use a finite amount of it, but at any time, but it's an unlimited, you never run out of space, working space you use in case you need some more. And the other thing that's unlimited is essentially time. You might keep on running forever. So you have the finite tape alphabet, which must contain the blank symbol that you the tape can be, every tape square can be blank. We have the finite set Q of states, and we have the transition function. And the transition function is a function that assigns to a pair consisting of the current state and the current symbol we're looking at on the tape, a triple of information, which is the new state. So for every such pair, you specify the new state that you move into, the new tape symbol that you write on top of the previous tape symbol. On the example Turing machine we were looking at before, we never changed the tape symbol, but in general you might write a new symbol over the top of the current symbol in place of the current symbol. So this is the new tape symbol. And then one of 3 instructions on how to move the head. It's very local, you don't jump around. You either stay where you are, that's 0, move left, that's -1, or move right, that's +1. So let's say left, right. I won't bother writing on 0. That's stay put, if you like, stay where you are. It's a partial function because we don't need, you don't necessarily have for every, if you're given a particular pair of state and symbol you're looking at, there can be at most one thing to do with it, at least with the current kind of Turing machine, a so-called deterministic one, in which it's precisely specified what you do. But there doesn't need to be anything that you do. So for some states and symbols, you might just do nothing, in which case the Turing machine holds. And we already saw that with the accept and reject state here. There are no transitions out of accept and reject states. So that's why it's a partial function. Okay, so maybe just write. So what this means, partial function, is for every pair, for every QA, for every pair of state and tape symbol, there is at most one, Q prime, A prime, D for plus or minus, for -1, +1 or 0, such that delta of QA, so there's most one instruction for it, delta of QA equals Q prime, A prime, D. Or in the notation I was writing before, I was writing this as QA arrows to emphasize that this is like a transition from a state with this symbol to the new state, Q prime. My writing is getting a bit messy here. Q prime, A prime, D. Okay, so it's a good time to break. Let me pause the recording. Right, okay, so we're now starting the second hour, and in order to do that, I'm going to begin by sharing my screen. So we're now screen sharing, and let's go to get that out of the way. Okay, so to specify a Turing machine, as we've seen, we need to give a little bit of information, a finite alphabet that we're using to decorate the tape symbols, the set of states that we're going to use for the Turing machine, and the transition function that tells the machine what the steps of computation are from the current position of from the current symbol that we're seeing on the tape. That's the symbol in gamma here, and the current state we're at. And because the sets of states and the tape alphabet are both finite, the partial function is itself a finite amount of information. And then once we've defined the machine, we've seen how it computes, but we need some mathematical terminology. I was already using it. At any step in the computation, we talk about the current situation that the machine is in as the configuration of the machine. So we don't use the word, one might informally refer to the state of the machine, but we don't use the word state because the state of the machine refers to which state symbol we're in. So which the machine is in one of these finite sets of states, one of these. So in this particular case, one of these finite sets of states for this machine. But we're interested in the whole configuration of the machine at a given point in the computation. And the configuration consists of the state we're at, the position that the read symbol is, the read write, sorry, not the read symbol, the read write head is looking at on the tape. And the other important information at any time in the computation is the whole of the content of the tape at that time. So we're interested, so the configuration of the machine during a computation at a particular point in time requires three pieces of information: the state, the current state, little q, the tape configuration. So the tape configuration is would you mind shutting the door, please? Thank you. So the tape configuration is so let's write this in blue because it's a bit informal. So the tape is decorated with finitely many squares being assigned symbols in gamma. So basically what I want to say is there are finite, and I should have just written it in these simple terms, there are finitely many non-blank squares on the tape. But we're interested in the whole configuration of the tape, so namely the precise description of what symbol is on every square of the tape, but only finitely many of them are non-blank. Being assigned non-blank symbol, it's finitely many squared being assigned non-blank symbols.
Or at all times?
At all times. So at the start, only finitely many squared. So the question was whether this applies just at the start of the computation or at all times. But if you start the computation with only finitely many non-blank squares, then at any step in time, you can only change one square of the tape. So at any square in time, it will always hold, at any step in time, it will always hold that only finitely many squares are non-blank. So the tape is decorated with finitely many squares being assigned non-blank symbols. So mathematically, we can, if we want to, we can model T. Well, we can, because it's an infinite tape in both directions, we can simply use the integers to index the squares of the tape. So we can simply model T as a function from the integers to gamma, that is blank, that takes the value blank on almost all integers. So on all but finitely many integers. On all but finitely many integers. But you shall almost never need to think of the tape as a function. We'll just talk about this, the current, where the tape head is and what the current read symbol is and so on informally. But if one wants to model it mathematically in formal mathematics, then that's one way of doing it. So T is a tape configuration. And the third piece of information we need, I, is the head position. So I is the position of the head at the current point in time. I is the position of the head. Read-write head. So again, if we're modeling the tape as being indexed by the integers, then the head position will just be an integer, which is the index of the current square. So if we want to do that mathematically, we can take I is the integer, which is the index of the current square that the head is looking at. And then the execution, again, one can give a precise mathematical definition of this, but having seen how it works in practice, I hope you don't mind not seeing the precise mathematical definition of how it executes. You just need to understand how it works. And we'll see some more examples in practice in the third hour, in the seminar hour of today. So the Turing machine execution is we start the machine on a tape configuration T that already contains some input. And the input is given as a word. So a word here is by a word, I'm going to use gamma star to be the set of words over the alphabet gamma. So by word, I just mean a finite sequence of symbols from gamma. So this is the set of words over gamma. So the input is given, so a word, maybe I'll write this at the bottom. A word is a finite sequence of symbols. And some notation. Well, let's give an example. So the input we used before, ABA, that's a word in the set of words over the alphabet the alphabet AB. So that's one example of an element of this set, but very importantly, I'm going to use a little curly epsilon as the empty word. So a word is a finite sequence of symbols, and that includes the empty sequence. So this is the empty word. So last week, Greta Thunberg accused the world leaders of speaking empty words, I believe. So maybe one should use the epsilon in that context too. Yes? It's not the power set. The power setter would be the set of all subsets. This is the set of finite sequences. So ABA is a finite sequence. Well, a word, a subset is just a collection of sets whose only elements are either A or B. So there would be 4 subsets here. So the empty set, the singleton set that only contains A, the singleton set that only contains B, and the whole set itself AB. So the set AB has 4 subsets, but it has infinitely many words from it, because there's the empty word, there's the word a, there's the word AA, the word AAA, and also the order is important, not just the number of times things occur. So mathematically, the set of words is the free monoid over the set. But to know that, you need to know what a monoid is, and I don't want to go down that route, but that's one way of describing it. But one just thinks of it as the set of finite sequences of elements from this set. But even with a finite set, the set of words is infinite, because you can have words that are arbitrarily long. So the point is, the input is given as a word, as we saw on the tape, and the machine starts in the start configuration. The machine, starts in the start state with its head pointing at the leftmost symbol of W, of the input word. So here one can make a fussy objection if you want to. There's a natural question to ask. As I'm allowing the empty word, you could say, well, where does the machine head start if the input is the empty word? Well, if the input is the empty word, the whole tape is blank. It actually doesn't matter where the machine head is. It's just somewhere. The point is, the machine can tell that we've got the empty input word because it's looking at a blank square. If the machine's not looking at a blank square, then we have a non-empty input word, and the machine assumes, because we start it in the right start configuration, that it's looking at the leftmost symbol of its input word. Okay. So once we've done this, we've started in the right starting configuration. This is the starting configuration. So maybe I should write here the start configuration. Starting configuration. Just as well say start configuration. Once we know the start configuration, we know the rules for how to compute. We've seen the example. We'll see some more examples. You'll also be looking at this in the exercise class. So now we understand how the machine is going to operate and how we give it as input. Okay, so that's pretty much the extent to which we're going to be going into the formal mathematics of Turing machines. But the example machine I gave you does a little bit more than that. There was a little bit more information, and that's to do with the precise task that we're asking the Turing machine to solve. And this task is to do with recognizing words. So actually, in the case that we're mainly going to be interested in this course, we have a little bit more information than we've given so far with the machine. So the idea is that we're going to use a machine to give it an input word, and we want the machine to tell us either do we accept this word or do we reject this word. And in order to do that, we actually normally, we don't just have the tape alphabet, but we look at a particular distinguished subset of it, which we call the input alphabet. So this is the alphabet from which we're interested in forming the input words. So in the case of our machine, if we go back to it, our input alphabet, we don't want our input words in this case to contain the blank symbol. In fact, we never want our input words to contain the blank symbol. The blank symbol is sort of padding out the space on the tape. And it's also useful if we don't have the input word containing the blank, we can go to the first blank and we know we've got to the end of the input word. We can go to the right to the blank. So we can use the blank as a way of detecting the end of the input word. So in our case, of this machine, the input alphabet is just the rest of the tape alphabet apart from the blank symbol. But in some cases, it's useful to allow the tape alphabet to contain other things too. So for example, if you're doing a really complicated calculation, you might want to record some information, some working information on the tape that's in a different alphabet from the one you're using for the input. So for that reason, you potentially allow gamma to contain some other symbols that are not in the input alphabet. But what we do want to know is when we give a machine, we want to know what alphabet our inputs are allowed to be from, and that's the purpose of this capital sigma here. So when we're looking to see whether we accept a word, we have a distinguished input alphabet, and we have distinguished states accept and reject. Because the idea is we want to say for an input word, do we accept the word or do we reject the word? So here we had that in our example. In our example Turing machine, we had the distinguished states accept and reject, and they were halting states. That meant when we got into those states, the machine stopped. And what that means is we don't have any transitions coming out of those two states. Okay, when we have a halting state, we don't have transitions coming out of those states. So we're particularly interested in machines in which, in addition to the tape alphabet, the set of states, and the transition function, we also have a distinguished input alphabet, and we have these two particular halting states, accept and reject. And then the idea is we give the Turing machine as input a word over its input alphabet, and we run the machine from that input word. So from the correct starting configuration in the state start, with this word as the only non-blank part of the tape written consecutively on the tape, and with the head pointing to the leftmost symbol of this word, if it contains any symbol, otherwise the head just points to blank necessarily. And the Turing machine is said to accept the word if, when we run the Turing machine on the word, when we run the TM, so sorry, TM is short for Turing machine. When we run the TM on W, the computation ends in, so stops in the reject state, sorry, in the accept state. And we say that the Turing machine rejects the word W if all the same stuff, when we run the Turing machine on W, on the input word W, the computation ends in the reject state. And what we're interested in is we're going to be interested in problems where we give the problem in such a way as, does the Turing machine, so we're looking at a particular alphabet from which we take the input words, and we're interested in, do we accept this word or do we reject this word? And the idea is we're going to code problems such as the three colorability of a graph that we looked at last week. We'll code it by, we give the graph as a word in over some alphabet that we've chosen the alphabet so we can nicely code a graph as a word. It's just like coding a graph as a word is just like presenting a graph. If you're going to present a graph to a computer, ultimately it needs to be converted into binary because computers use binary representation, and binary binary representation is just words over the alphabet 0, 1. So basically, we're familiar with the idea that to present a problem to a computer, we need to code it as a word over an alphabet, namely the alphabet 0, 1. Here we're going to be a bit more flexible. We allow ourselves to give convenient alphabets for the problems at hand. They're just a finite set of characters, but nonetheless, we're going to present problems as words. So we'll code, say, a graph as a word over an alphabet. We present that word to the Turing machine, and the idea is we write the Turing machine so it will say accept if the graph is 3 colorable and reject if the graph is not 3 colorable. So that's how we're classifying, how we're solving the problem. We're viewing it as accepting or rejecting a word, accepting or rejecting a word. Now, the standard terminology for this, there's a sort of linguistic terminology associated with this. So we're looking at, we're giving words over an alphabet. Some of them are accepted and some of them are rejected. And in analogy with natural language, computer scientists and mathematicians call such a set of words, the set of words that are accepted, we call that a language. So you can, it's a bit like identifying, say, the Slovene language with the set of words in the Slovene dictionary, or better, the Slovene lexicon, for example. So a language is a set of words. So here we're interested in the question, give the machine a word, does it say accept or reject? Another way of looking at that is give the machine a word. Does this word belong to the set of all words that we want to be accepted? And that set of words is a language, according to the mathematical terminology. So this idea, the Turing machine is accepting or rejecting words. We can equivalently view that as recognizing the language that is the set of words that are accepted. So a language is just a set of words. So that's a subset of the set of all words over the alphabet. And for any Turing machine that fulfills these conditions, that we have the distinguished input alphabet and we have the accept and reject state. In fact, we don't even need the reject state for this. There's just a standard thing we talk about. For such a Turing machine, we can say the language recognized by the Turing machine is just those words that if we give the machine the word W, the Turing machine accepts the word. It's a set of all words accepted by the Turing machine. So any Turing machine with accept and reject states for which we distinguish an input alphabet, any Turing machine will determine a language, namely those words that are accepted. The problem with this definition is we can accept a word by running a Turing machine and seeing that the Turing machine accepts the word. And we know that we're saying the set of words that are accepted, we're saying that's the language of words. That's the language of words recognized by the Turing machine. So we know that every word and only those words in the language will be accepted. But the problem with that definition is that if we run the Turing machine on a word that's not in that set, that's accepted, well, the Turing machine might end in the reject state, that's fine. But according to this definition, it doesn't have to. It might end in some other state, or even worse than that, it might just keep on computing forever. And maybe we can see that our machine is still computing, it's sort of whirring away, moving its tape left and right and performing. And we might be wondering, the machine is computing, we might be wondering, is this word in our language? And the machine's still computing, and we can't really ever say it's not in the language because the machine's still computing away. If we might give up and say, well, the machine's not given us an answer, but still the word might actually be in the language. We just weren't patient enough to wait long enough for the Turing machine to get in its accept state. So it's much better to be in a situation. So this is, for any Turing machine, we can define the language recognized by the Turing machine, but we're much happier if we're in a situation that we know the Turing machine is going to halt for any word we give it as input, any word from the input alphabet, and that it will be in an accept state when it halts for only the words that we're interested in. And if we give it another word that's not in the language, well, then it will halt in some other state. And for good measure, we might as well require it to halt in the reject state. We could always, if it halted in some state different from the reject state, we could always add some more instructions to the machine to put it into the reject state anyway. So we can always get it to halt. We can always get it that if it halts either in the accept state or the reject state. And what we would really like to be in is, if we're interested in knowing the answer to our question, given our input string, is it in the language or not? Given our input string representing a graph, is it three-colorable or not? It would be really nice to know that one way or another, we're going to get the answer accept or reject, so we will know which way round it is. And that's this second definition here. So it turns out that not every language can be recognized by a Turing machine. And even for those languages that can be recognized by a Turing machine, not every language can be recognized in such a way that we're guaranteed to get an accept or reject answer. The most famous language that can't be rejected by a Turing machine that's guaranteed to be given an accept or reject answer is what's called the halting problem. And that's, we code up as an input word, we code up a Turing machine, and then the Turing machine we're running to try to solve the problem is supposed to tell us whether the Turing machine we've coded up as an input word would halt or not, if given, say, the empty input. That would be one way of configuring the problem. And that is a problem that it's impossible to have a Turing machine that is guaranteed to accept or reject depending or not whether the input word represents a Turing machine that halts or doesn't. So these issues I'm talking about now are basically the topic of computability theory, which is a different course, which in fact I taught last year, and some people here took that course. So I'm not going to really talk around that very much. For this course, what we're interested in are problems for which are not like the halting problem, but problems that are mathematically well behaved enough that we can find an algorithm that's guaranteed to halt for them. So it is possible to find an algorithm that is a Turing machine that, when given an input, will tell us, yes, the input is accepted, or no, the input is rejected. So three-colorability is like that. There's a Turing machine, a very, very inefficient one. There's a Turing machine that searches through every possible way of coloring the nodes of a graph in three colors and checks for each one if it is actually a three coloring. So if no two adjacent vertices have the same color. Very efficient, very inefficient. It has an exponential runtime in the size of the graph, but nonetheless, it is an algorithm. And if one's patient enough, it will give you an answer, a yes, no answer. And for the whole of this course, we're going to be only concerned with these kinds of problems, that there exists an algorithm, that we can find algorithms that either accept the word or reject the word if it's not in the language. So these problems are called the decidable problems. So I've just got, these notes have a bit of supplementary information here that's not particularly relevant to the course, but I wanted to show it you for context. But the point is, this course will be concerned with decidable languages. So the halting problem I mentioned, that's a fundamental limitation in computability. It turns out there is no way to produce a Turing machine which will halt if the input represents a Turing machine which will say halt and accept if the input represents a Turing machine that halts, and will halt and reject if the input represents a Turing machine that doesn't halt. That's a fundamental limitation. For the problems we're concerned with, we're only going to be concerned with problems that are decidable. There does exist a Turing machine which will either halt and accept or halt and reject. But this course is going to be concerned with other fundamental limitations, because I've already mentioned for the 3-color ability that we have such a Turing machine. I've outlined to you at a very high level that it will just search through all colorings and check each coloring to see whether or not it is a legitimate 3-coloring of the graph, but that's very inefficient because there are exponentially many colorings in the size of the graph. And the point is that we're going to find out there are other fundamental limitations here, because although we can decide this problem, it seems, and this is related to the P equals NP question, it seems that there's a fundamental limitation. We cannot really decide this problem efficiently, although we will discuss that in future lectures. Okay, so we're going to be concerned with decidable languages. So that's one of the important things we use Turing machines for, recognizing languages. Another important use of Turing machines is to compute functions. So that's something else. So an important aspect of computation is solving a problem. Does this, here we've got an instance of a problem, does it fall into the class of such problems that satisfy the condition we want, or does it fail to satisfy the condition we want, such as 3-color ability? But another important class of computational problems is computing functions. So, for example, given some, well, a famous example that I already mentioned last week, given a large integer, compute a prime factorization of the integer, or the prime factorization of the large integer. That's not a decision problem, although it can be encoded as one, which we'll talk about that later on in the course. But fundamentally, that's a problem that's asking us to compute a function. Given an input, produce some output that's more interesting than accept or reject. So how do we use a Turing machine to compute a function? Well, as you can imagine, this is rather intuitive. So we are interested in because Turing machines work with words, so with their tape alphabets, we're going to work with words, and we're going to consider a Turing machine as a function. If we want to consider a Turing machine as computing a function, we want to consider a Turing machine taking a word as input and giving us a word as output. And then we can talk about, say, functions on the natural numbers or other kinds of things by encoding natural numbers as words, for example, using a binary representation, or even a base 10 representation is a representation of numbers as words. Okay, so we again assume we've got some distinguished alphabet of symbols that we want this time to use both for the input and the output, because we're transforming words to words. So again, assume a distinguished, but this time a distinguished subset of the tape alphabet not containing the blank symbol. So this, by the way, the backslash here is my set difference operation. So I'm here removing the blank symbol from the set of tape symbols. So the alphabet is a subset of the non-blank symbols. So this is called this is now not the input output not the input alphabet, but the input-output alphabet. And the important definition is to say when a Turing machine computes a function f on words over sigma, which is both, so it's both the input and output alphabet. So we give an input word over sigma and we get back an output word over sigma. So we say that a TM computes a function f such as a complicated example would be a function over a suitable alphabet that we can give a large integer in, and the function will return some suitable word that represents the prime factorization of the large integer. But we're interested in functions from the set of words to the set of words. So it computes a function if whenever, it's just the obvious thing, almost, whenever we run well, in fact, it can just be the obvious thing. Whenever we run the Turing machine on an input W in sigma star, it halts with f of W on the output tape on the tape. There's only one tape. And what do I mean by this? Well, just as we had W on the input, symbol by symbol, left to right, and all the remaining squares blank, I want f of W on the tape, written left to right in adjacent squares, with all the other squares on the tape blank. Okay, so f of W on the tape and all other squares blank. And if we want to be fussy, we can also require that the tape head returns to the left-hand symbol of f of W. And that's convenient if we want to compose Turing machines. So if we've got a Turing machine for f and then a Turing machine for g, and we want to compute g composed with f, so we first apply f to an argument and then apply to g. It's kind of convenient to run f first and then have the head in the right position to then start running g. So if you want to, so if we like, we can require the head position to be at the left symbol. But actually it doesn't, I mean, it makes a difference in that if you make this requirement, then there are fewer Turing machines that compute the same function. But still, whether or not one makes requirements like this, and there are other requirements that one could make, such as that the machine must halt in a distinguished state called halt or something like that. You can make such requirements too, but actually it doesn't make any difference to the next definition, which is that we say that the function f is computable. So what we're interested in is as well as a particular Turing machine computes a particular function, but we might be interested for a given function, does there exist an algorithm? Can we find some algorithm that computes that function? And if we can, we say the function is computable. So, in this course, we're only going to be interested in computable functions, and then we're going to look at the question, can we compute them efficiently? Or if not, to what extent can we say how hard it is to compute the function? So we say that f is computable if there exists a Turing machine that computes f, computes the function f. Okay. Right, so it's already 10 o'clock, so I think we should, it's a convenient point to make a break. So let's pause the recording. How do I do that? Oh, I need to stop the sharing. And remember to share screen. Right, so where were we? Right, so we've defined two very important things, what it means for a language. That's a set of words over an input alphabet to be decidable. That means we have a Turing machine, a way of computing that it will either tell us if an input word is accepted, belongs to the language, or rejected, does not belong to the language. And what it means for a function on words to be computable. And as we discussed in class in the break, actually, there's no reason necessarily to have the same alphabets here. You could transform some input alphabet to a different output alphabet. So I'll leave it up to you to make the appropriate modifications of the definition. But most often we will be interested in functions on words from the same alphabet to the same alphabet as defined here. And we've got the notion of what it means for such a function to be computable. Namely, there exists an algorithm that is a Turing machine that, given any input, will eventually halt, and on its tape it will have transformed the input string into the appropriate output string. Okay, so these definitions are the ones we need for the course as defined so far. But you might say, well, there have been so many arbitrary choices made in the definitions. Why did we define the Turing machine? So, okay, the general principles for the Turing machine seemed right, of having a finite description, being able to have some working space and as much working space as we need, and so on. But still, you can imagine many other different ways of implementing that. So without going too far, I mean, there are actually very wildly different ways of implementing it. But even while sticking to the kind of similar notions of machines, there are many other choices we could make. So let's consider some of the other choices we could make with the notion of varying Turing machines as we've got them, machines working on tapes with read-write heads and taking input words and potentially giving us output words and so on. So what variations could we have? Well, we could make the model weaker, or we could make it stronger. So just to mention one way of making it weaker, so a way of seemingly making the model weaker, we've got tapes that are infinite in both directions. Potentially, we can get an arbitrary amount of tape by pulling from the left, or an arbitrary amount of tape by pulling from the right. So we do need to always be able to call on extra space if necessary, but we could just make it infinite in one direction. So that would seemingly make the model a little bit weaker. And I'm mentioning this one because I didn't actually double check with the article, but I'm pretty sure that's Turing's original notion of Turing machine, has tape that's infinite in only one direction. But certainly the main reason for mentioning this is the main textbook for the course, the Aurora and Barak textbook, that uses a Turing machine, that uses Turing machines that are infinite only in, where the tape is infinite only in one direction. So that's a possible variant. The thing that's not so nice about that variant is you have to define the protocol of what happens if your head is at the left edge of the tape and you tell the head to go left. I mean, obviously it should stay in the same position, but it's a little bit, you know, there's a nasty case to consider there that you don't have if you have the tape that's infinite in both directions. So the other things, the other variations I'm going to mention for just for discussion are ways of making the model more seemingly more powerful. So here we've got, so far we've used one tape with one head, but it might be useful to have a bit more working space and be looking at more than one symbol at once. So one way of doing that is to have k different tapes for some number k greater than 1, and one head for each tape, the same number of heads. Or you could have machines with many heads per tape, and possibly even heads that jump between tapes if you've got many tapes. And you can imagine in all cases, it looks like you're making the machine a little bit more powerful. But one of the benefits of what we've got is the mathematical definition is relatively simple. And obviously the more bells and whistles, as one might call them, features that one adds, the more complicated the mathematical definition is going to be. So you'd want to, if you're going to make the mathematical definition more complicated, you want to get something back for it. So are we really, you know, if we make the model more complicated, are we really going to get anything back from that? And another generalization would, well, humans don't tend to work with one-dimensional tape. They tend to work with sheets of paper because that's what that's how paper works, and we can naturally work with 2D work surfaces. Even complicated ways we might work with 3 dimensions, but we can certainly easily work with 2-dimensional sheets of paper. So we might have 2-dimensional workspaces, or since we're giving mathematical definitions, we could mathematically quite easily boost the number of dimensions and consider multi-dimensional workspaces instead of 1-dimensional tapes. And then I'll just leave this to your imagination. So one could make other kinds of adaptations too. So the point is, I go to the pen, put it in blue. All such variant models, whether the weaker ones that have the infinite tapes only in one direction, or the stronger ones that have many tapes or multi-dimensional tapes and many heads and jumping heads and so on, all such variations turn out to be equivalent to our definition. What that means is an encoded a variant Turing machine can be transformed to an equivalent Turing machine as we've defined it. So for any variant Turing machine, we can find an equivalent one, but not only does an equivalent one exist abstractly, but we have a way of translating the variant Turing machines to the equivalent ones according to the definition we've given. So we have a way of translating between the different kinds of Turing machines. So a TM, in our sense, well, let's say any variant TM can be transformed to a Turing machine in our sense, and vice versa. And I'll come back to this statement either later today or next week to add something to it. But for now, we'll take it like this. So in some sense, we don't need to, well, in a strong sense, we don't need to consider such variant models. However, it will actually be useful for our course to consider one such variant model, even though it's equivalent to the Turing machine we've given, because for some purposes, it's going to be easier to talk about multi-tape Turing machines rather than single-tape Turing machines. So I do want to define the notion of a multi-tape Turing machine. So here we're looking at a 2-tape Turing machine. So what does a 2-tape Turing machine look like? Well, it's like an ordinary Turing machine. It's the same picture, except it's got 2 tapes, and each of the tapes has its own head, read-write head. So it's got, in general, K tapes and K heads. And once again, we start the computation running on the, we use one tape as the input tape. So here I'm using tape number 1 as the input tape and tape number 2 not as the input tape. Might use it as the output tape. It depends. You can configure things as you want, but we're going to start in the starting configuration. We've got, so the second tape is blank. The first tape has the input with the thing pointing at the left. And just as before, we've got a set of states. We've got the tape alphabet. I haven't bothered to write that out again, the input-output alphabet. We've got a transition function. And I'm not going to go through the whole process here. I just want to show you just a couple of steps how it works. So we start in the starting configuration. So again, on our input tape, on our tape 1 where we've got the input word, the head is at the left edge of the input word. The other tape's blank. And now we need to see how we make a step of computation. So now we're in a state, and we've got a symbol that we're looking at on tape 1 and a symbol that we're looking at on tape 2. So now the transitions have triples of information on the left, consisting of the state we're in, the symbol that we're looking at with head 1 on tape 1, and the symbol we're looking at on tape 2. And we see that we're in start, we're looking at A, and we're looking at blank. So this first transition is the one that fires. We're start, A, blank. So we stay in start. The first head keeps an A. The second head also puts an A on its tape. So now we need to write an A. Let's make that A look a little bit clearer. So now we write an A. The first head moves right. And the second head moves left. So we've written an A here. The second head is moving left. So there's another cell here that I hadn't written. So the second cell tape goes to here. Now we're still in start, we're at B and blank. So if we start at B and blank, then we stay in start, we write a B on the, we keep the B on the first tape, we write the B on the second tape. The first head moves right. And the second head moves left. And I'm not going to finish the computation. So this is going to be an exercise for you. Complete this computational process and see what you get. And the question is, which I don't want you to answer now because somebody might have seen this machine before. You'd have to be very quick to have read it all because I'm just scrolling through it. But the question is, follow the process and then answer the question, what language does this machine recognize. Okay, but what we've got from this is the idea of a two-tape machine. And in general, a K-tape machine has K-tapes, each with its own read-write head. So what that means in practice is now the configurations are a bit more complicated. The configuration is a state together with K-tape configurations and K head positions. Okay. And the other thing that's different is the transition partial function now has the form. So now the partial function, to make a transition, we look at the state plus the K symbols that we're looking at on each of the K tapes. And from that, this part means partial function. From that, we either do nothing, in which case we stop, or we assign a new state, K new tape symbols that we write on the K tapes, and K different movement directions, either move left, stay in the same place, or move right. And we execute the K tape machine in the natural way as illustrated in the example. Okay. So that's the notion of Turing machine, of K-tape Turing machine. What I want to end with today is one of the, or two of the most important definitions from the course. Because now we've got the mathematical basis for defining them. And then we are going to have like 20 minutes or so of seminar time, in which I'll stop the video and the seminar time will be looking at something online related to Turing machines. Right. So I just want to give 10 minutes now, the last 10 minutes of material in the lecture to introduce some very basic definitions of the course, very fundamental definitions to the course. So, so what I want to say, so this course is about computational complexity. So that's about looking at, for example, time complexity or space complexity for computational problems. And a basic computational problem is recognizing a language. So given a word, does it belong to the language or is it outside the language? And we're going to look at such problems and put them in complexity classes. So a particular problem, for example, the three colorability of a graph, we're interested in what complexity, well, for example, time complexity class that problem is in. So how quickly can a Turing machine run to solve that problem, more or less? So I'm going to leave a bit of space at the top for, so for a language, so if we've got some input alphabet, and we've got a language, that's a set of words over that alphabet. And the function t of n, this is a function on natural numbers, which we're thinking of a function of modeling number of time steps. We say that L belongs to the class of problems but with time complexity T of n. So people sometimes say time, and they sometimes say, to be precise, d time, where d means here deterministic. So let's keep the d in. because these Turing machines we've been looking at today are deterministic. That's whenever in any configuration, there's at most one step of computation they can do, because the transition was what we specified for the transition, that was a partial function. So L is computable in deterministic time t of n if oops, trying to get back to black. So if there exists a Turing machine that decides L, so that is, it recognizes L, and for words not in L, it always returns reject. So it accepts every word in L, rejects every word that's not in L. Such that for every possible input word, so every word over the alphabet sigma star, the Turing machine runs in time Tn. So it runs in time T of the length of the word W. So here we've got the length. So the point is, the function t is telling us how long the Turing machine runs in the size of the input word. So this is the length of the word, or the size, if you like, of W. Sorry, I just want to make that looked a bit messy, that length. So that's right, that's a bit neater. But I haven't told you what runs in time means. So runs in time. So here we're going to have many words of the same length. And if we look at the number of steps the Turing machine takes, it might take different numbers of steps on words of the same length. So what does this runs in time mean? So we say, so what it means is that for every word, the number of steps taken by the Turing machine is less than equal to t, the function t applied to the length of the word. So the function t is giving an upper bound for the worst case runtime of all words of that length. So we say that a Turing machine runs in time Tn if for any input word of length n, let's say every, just to make it clear that this is a universal, if for every input word of length n, the Turing machine halts after at most Tn steps. So the informal explanation is Tn, the function t of n, is an upper bound for the worst case runtime of the Turing machine. Okay, so So we're looking for functions that bound the running time of a Turing machine in terms of the length of the input. And notice that we're defining then a set of languages. For any function t, we're defining, on natural numbers, we're defining a set of languages of those languages that have a decision procedure that runs in time of that function. And now the fundamental definition is going to be the definition of polynomial time computable functions. So let's put it in black. Fundamental definition. The problem class P, those problems that are computable in polynomial time, this is the union over all d from the integers of deterministic time of n to the d. So it's those problems that are solvable by a Turing machine as we've defined it, either in d time n or d time, oops, I should also, let's allow a constant in here. Just give ourselves a, so in some time bounded by some monomial, and because one can always make asymptotically monomials large enough, or we've got the factor of c here as well, then we can also bound any polynomial in this way. So this is enough to bound. So any Turing machine, any problem that's decidable by a Turing machine that has a polynomial time bound will be in this class. And because we're using explicit polynomials in the definition, only such Turing machines in this class. So the those languages that are decidable in polynomial, deterministic polynomial time. So I could write that down. The language is decidable in deterministic polynomial time, but I think, you know, you can get that phrase. You can run the video back if you want to get that phrase, but I think it's clear. Okay, so just to make one more point before we end the lecture material, and then we've still got 15 minutes for the seminar. It's a very short seminar today, but we'll have a look at the seminar. So we will do this. So just one point to make: this language P does not depend on the notion of Turing, the notion of Turing machine that I used. So those variants, I said they were all equivalent, but they're all equivalent. You can translate between them. And those translations make only a polynomial difference to the runtime. And because they make only a polynomial difference to the runtime, this definition, which is up to, basically up to a polynomial equivalent anyway, we're looking at an arbitrary polynomial bounds. So if you transform the runtime by a polynomial and you were in this definition before, you stay in the definition. If you're outside it, you stay outside it. So I should just add that to where we talked about. So moreover, this translations, such translations, that should be an L, involve only polynomial factors in change of runtime. So one of the fundamental reasons, so polynomial time is supposed to be kind of corresponding to, roughly speaking, efficient computability, but one of the, you might say, time n to the power of 100, that doesn't look very efficient. So actually it turns out that if an algorithm is in polynomial time, we tend to be able to find an algorithm with a low exponent. That just happens to be the case. It has happened to be the case historically. But the fundamental mathematical reason for considering arbitrary polynomial runtime is that by doing so, we make the definition independent of the choice of computational model. It doesn't matter which notion of Turing machine we take. It doesn't matter if we take some other model of computation that's not a Turing machine. However we do that, if we define runtime in a reasonable way, then when we make the definition of the polynomial time computable languages, we will always get the same definition of the same languages will count as polynomial time. It's a really fundamental mathematical notion. Right, good. That's the end of the lecture material. So I'm going to stop sharing my screen and stop the recording. And we're now going to have a short seminar part, which is not going to be recorded. So that's the end of the recording.